Lesson 10.1 is about arcs and sector, and by the end of this lesson, we're going to have a few formulas that we are going to be able to not only understand how we come up with them, but be able to apply them to a few problems. Let's begin exploring the properties of circles by looking at the following diagram. We say that APB is a central angle because of two reasons. One, it is composed by the two radii, in this case they would be AP and BP, and two, the vertex of the angle is the center of the circle. Remember that in a circle, point P is not called the middle of the circle, instead it's called the center of the circle. Because APB is a central angle, it ends up splitting the circle into two arcs. A smaller arc, AB, which we're also going to call a minor arc, and a much bigger arc, ACB, which we're going to call a major arc. A property of central angles is that a central angle and its corresponding minor arc are always equal to each other. And we can even go into a little bit more detail and ask what are exactly the differences between a minor and a major arc. So if you remember in a circle, the total measure is always going to be 360 degrees. Given what we just finished saying, I hope that you agree with me that the total arc measure also has to be 360 degrees. Well, any arc that is less than a semicircle, and a semicircle is half a circle, so half of 360 degrees, 180 degrees. Any arc that has an arc measure less than 180 degrees is going to be called a minor arc. Similarly, any arc that is greater than a semicircle, in other words, any arc that has a arc measure that's greater than 180 degrees is going to be called a major arc. And already we can start solving simple problems like we have in example 1. So for example 1, we're given the following circle, center at W, and we are asked to find the measure of arc XZ and the measure of arc XYZ. In order to solve for the measure of arc XZ, well, I know that the measure of arc XZ has to equal the measure of its corresponding central angle, and I know that XWZ has to be a central angle because it's composed of two radii, XW, ZW, and its vertex is the center of the circle. So it has to be, by definition, a central angle. I further know, because it's right there on the diagram, that the measure of angle XWZ is 115 degrees, so it has to be the case that the measure of arc XZ is 115 degrees as well. To solve for the major arc XYZ, well, the total arc measurement has to be 360 degrees. So if I take away the measure of arc XZ, I should be just left with the measure of arc XYZ. Previously, I found out that the measure of arc XZ is 115 degrees, so 360 degrees minus 115 degrees gives me a total of 245 degrees as the measure of arc XYZ. But the real fun part begins when you want to calculate the arc length of a circle. Arc length is just the length of a little bit of the circle. So if you look to the left, if you wanted to calculate how long the orange curve is, you would be calculating an arc length. And the way that we're going to be able to calculate for arc length is by using a formula that we're going to develop by following the following line of reasoning. I know that the arc length is some fraction of the entire length of the circle. The entire length of the circle gets a fancy name. It's the circumference of the circle. I also know that the arc measure of the arc is also a fraction of 360 degrees. Those two ratios are going to be equal to each other, so I set them equal to each other in an equation that I have on my right. Replacing arc length with a variable s, replacing arc measure with a variable n. There's nothing special about those two variables, it's just what we use. And the fact that we can calculate the circumference of circles by using the expression 2 pi r. S over 2 pi r is going to equal n over 360. Moving things around, multiplying both sides by 2 pi r, I get the following expression. Arc length is equal to n divided by 360 times 2 times pi times r. And this is the formula that we're going to use to calculate the length of an arc. However, this will only work if the angle n is measured in degrees. The other popular way of measuring angles is to use radians, and all a radian is, it's a central angle whose corresponding arc has an arc length that is equal to the radius of the circle. That definition sometimes tends to trip people up the very first time that they hear it, so if that doesn't make sense right away, don't worry about it, let it marinate for a little bit. What we want to do is come up similar to what we saw before, come up with an equation that we can use to calculate the arc length of any circle, even if they are in radians. And luckily, the logic is pretty much the same. Arc length is going to be a fraction of the circumference, but now because we're in radians, the overall arc measure of the circle is not 360 degrees, it's going to be 2 pi. There are 2 pi radians in every circle. So arc length divided by circumference is going to equal arc measure in radians divided by 2 pi. Replacing arc length with s again, arc measure with the Greek letter theta, just to make it a little bit different from degrees. S over 2 pi r is equal to theta over 2 pi. Using the beauty of algebra, multiplying both sides by 2 pi r and isolating s, we get s is equal to theta divided by 2 pi times 2 times pi times r. And then notice that we have repeating terms in the numerator and the denominator. So arc length simplifies into the arc measure in radians multiplied by the radius of the circle. And this is the formula for calculating the length of an arc, but only if the arc is measured in radians. Let's take a look at a problem that requires us to apply all of that knowledge. We want to know what is the length of arc AD, and I want to express my answer in terms of pi. It looks like, according to the diagram, that the central angle BPA is 73 degrees, the central angle BPC is 43 degrees, central angle CPD is 104 degrees, but I don't know what the central angle APD is, and that sucks because if I don't know what that central angle is, then I cannot find the arc length AD, because arc length requires you to know the corresponding central angle. So I have to do two things. First, I have to find that arc measure. I know that if I add up all of the arcs, they have to equal 360 degrees. So the measure of arc AD plus the measure of arc AB plus the measure of arc BC plus the measure of arc CD, all of them added up have to be equal to 360 degrees. Manipulating things around and trying to get the measure of arc AD by itself, which is really what we care about. We have 360 minus all the other arcs. Substituting actual numeric values for those arcs, I get 360 minus 73 minus 43 minus 104. So the measure of arc AD has to be 140 degrees. Now that I know that the central angle is 140 degrees, finding the arc length is just a matter of using the formula we just saw. Arc length is equal to n over 360 times 2 times pi times r. I'm using this particular one again because we are dealing with degrees rather than radians. N is the central angle, 140. R is the radius. In this case, it happens to be 4. So putting everything where it belongs and following the computation, I get 28 over 9 pi. We wanted to leave our answers in terms of pi, so we're not going to multiply by pi. Working with radians is not that different. So let's say that instead I wanted to find what is the length of arc JK, and I still wanted to express my answers in terms of pi. I will follow the same process. First, I need to know what is the arc measure of JK. I know that the measure of arc JK has to equal the measure of its corresponding central angle. Looking at the diagram, that's going to be angle JQK, and JQK is 3/4 pi radian, so the measure of arc JK also has to be 3/4 pi radian. Once I know the measure of the arc, then all I have to do is apply the formula for finding arc length. The measure of the arc times the radius. My answer is going to be 3/4 pi times 5, which is the radius, which simplifies into 15/4 pi. Again, keeping that pi there and not multiplying by it. When it comes to circles, we're also interested in being able to calculate the sector of a circle. And all a sector is, it is a region bounded by two radii, in this case MQ and NQ if we're looking at the diagram, and the intercepted arc that they create. It has to be the case that the area of the sector, which is the area in yellow, and I'm going to represent that by using the letter A, the area of the sector has to be some fraction of the total area of the circle, and it has to equal the relationship between the arc and the overall arc measure of the circle. So written out algebraically, A, area of the sector, divided by the total area of the circle is going to equal the arc measure divided by 360. We have seen before that the total area of a circle can be found by using pi r squared, so replacing total area with pi r squared, and then multiplying both sides by pi r squared allows me to develop a formula that I can use to find the area of a sector. Area is going to be n over 360 times pi times r squared. Applying it to this particular example, n is going to be 78, r is 10, so 78 over 360 times pi times 10 squared, you're going to get 65/3 pi, and that's going to be the area of the sector. Lastly, we need to cover segments. A segment, if we look at the diagram on the right, is the region bounded by the curve MN and the side of the triangle MN. And the way that we're going to tackle this problem is first we're going to try to find the area of the sector. Then we're going to find the area of the triangle. And then I'm going to subtract the area of the triangle from the area of the sector in order to find the area of the segment. So my very first step is to find the area of the sector. I know that I can find the area of a sector by using the following formula. N over 360 times pi times r squared is going to give me the area of the sector. N is going to be the measure of the arc, and r is going to be the radius of the circle. I know that n is 90 degrees. How do I know that n is 90 degrees? Well, if I look at the diagram, the central angle MQN is 90 degrees, so it has to be the case that its corresponding arc, MN, is also 90 degrees. So 90 minus 360 times pi times 10 squared equals 25 pi. Now that I have the area of the sector, and I'm just going to leave it in terms of pi for now, I need to find the area of the triangle. That's my second step. And this is going to be the most involved steps because most likely than not, you're going to be using trigonometry. I'm going to take the triangle that's on the right and I'm going to redraw it again. I know that in order to find the area of a triangle, I have to use base times height divided by 2. This triangle on the left is the exact same triangle that I have on the right. It is triangle NQM. If I draw an altitude from angle Q to the side NM, making a 90-degree angle because it's an altitude, then I'm going to do two things. I'm going to bisect the angle NQM, which was originally 90. 90 divided by 2 is 45 degrees. And I'm going to bisect the side that I make a 90-degree angle with. So I'm going to bisect NM. I'm going to cut it in half. Looking at the diagram, I end up having a right triangle. And I'm going to use that right triangle to solve for x and h. H is going to be the height of the triangle. X is not going to be the base of the triangle, but is going to help me find the base of the triangle. Because if I know the value of x, all I have to do is multiply it by 2, and then that's going to be the base, which is little b. Okay. Using trigonometry, sine of 45 degrees is equal to the opposite side divided by the hypotenuse. Multiplying both sides by 10, I get x is equal to sine of 45 degrees times 10. Sine of 45 degrees is the square root of 2 over 2. So the square root of 2 over 2 times 10. X is equal to 5 times the square root of 2. To find h, now I'm going to use cosine, which is adjacent over hypotenuse. Multiply both sides by 10. H is equal to cosine of 45 degrees times 10. Cosine of 45 degrees, just like sine of 45 degrees, is also the square root of 2 over 2. So h is equal to 5 times the square root of 2. Remember that the base is not x, but the base is 2 times x. So if x is 5 square root of 2, 2 times x is going to be 10 square root of 2. So base is 10 square root of 2, height is 5 square root of 2, multiply them together, divide by 2, 10 times 5 is 50, square root of 2 times the square root of 2 is simply 2, 50 times 2 divided by 2 is going to give you an area of 50. So the area of the triangle is 50 feet squared. Lastly, just to find the area of the segment, I take the area of the sector, which was 25 pi, and I subtract 50 from it. Area of a segment is equal area of a sector minus area of a triangle. 25 pi minus 50, and then that's going to be approximately 28.5 feet squared. And in summary, this is a nice chart that shows everything that we've done so far. When it comes to arc length, you have to remember when to use one equation versus when to use another, when you have degrees versus when you have radians. When it comes to sectors, the most important part would be the radius squared. People tend to forget to do that when they multiply. If you just multiply by r, then that's not the correct answer. Segments, the most complicated part is probably always going to be the finding the area of the triangle, because you're going to be using trigonometry. If you are having trouble with the trigonometric stuff, there are many resources that you can easily look up on YouTube, for example. If you want to ask for specific things from me, just let me know. And that is everything from this section.